Right, good evening. Apparently and allegedly, quite a number of people said they wanted me to bring back Twilight, and which I have done. And as you might be aware, we've not done Twilight for quite considerable time. And we did have 180 on the day at the last Saturday event. So you guys are wanting the Twilight. You're going to have to do better than this, not you. You know, kind of tell people to go for it. But we're very fortunate because we're going to be recording this, and hopefully it will go across the board, across the education, and that's what we want. So I'm going to be very brief about this and introduce Aidan. I'm sure there is nobody here who doesn't know Aidan. He's been working with schools education for quite some considerable time, and his particle physics talk is pretty good. I've heard it before. So just Aidan.
Right, thanks, Ronna. Well, it's nice to see you all. First, just a quick advert, actually. So for the particle physics masterclass, this is I think the 6th year I've done this, and it's happening on the 17th of June. And I hope that most of you will have seen the invitation on Sputnik. If not, just go and have a look. And if you search for masterclass, then you should find it. It's a whole day. It's an introduction to particle physics, and I think it's a nice way for your students who are just starting their 6th year course, first to get excited about particle physics, but also just to spend a day in a university and have a sense of what that's like. And people seem to enjoy it. So I encourage you to bring pupils, or even just to send them. There are some places left, and just email me here if you want to do that. Right, so the main thing is to talk about particle physics. And I feel like I've given a talk like this really quite a lot. Ronna tells me it's the talk that is wanted, but I just apologize if you've heard a similar talk from me before. The slides that I'm going to use are a very similar set, are already on SBTR. So if that's a useful thing for your teaching, then please look for them there. I think there's a folder that's CPD and then Aidan, Robson, and you'll find them there. So the idea, since particle physics, I think, is featuring a bit more in secondary school syllabuses, is just to give you my perspective on particle physics. What I think, as a particle physicist working at Hadron Colliders, we're trying to do, what it's all about, and why we need the tools that we have, the accelerators and the detectors, and just give you what is maybe a slightly different perspective on this from what you maybe had before. So, I mean, first of all, the biggest question, what we're trying to do, I mean, if you try to explain the universe at the most fundamental level, you can think of different ways of approaching the problem. So you can look deep out into space, and of course, you're looking back in time towards the Big Bang and try to understand how the universe works at the sort of biggest structures and infer the underlying physical laws from that. So that's looking at the universe on the biggest scale and back in time. An alternative approach is to try to look deep inside matter. So here's a sort of cartoon of an atom. There's a cloud representing the probability of finding an electron there. Then the nucleus, this is 2 protons and 2 neutrons, looks like helium. And we're going to go inside now one of the protons or neutrons. And what we see is that the simplest description of a proton or a neutron is that it's made of 3 distinct components, 3 quarks. And so this idea of looking deep inside matter and trying to understand things from the fundamental level, it sounds a kind of opposite approach from looking into space and trying to understand the biggest structures. But it turns out that the approaches are very closely related, and especially when we talk a bit about the Higgs boson towards the end, I hope you'll see that. So particle physics, it's a bit like a Lego approach to understanding physics. It's trying to understand what the fundamental building blocks are and then how they go together to make more complicated objects. So if we start trying to write down what those basic building blocks are, I've said already that inside a proton or a neutron there are 3 quarks, and they come in different kinds, so they're up and down quarks. And the electron is the other thing that you need to build an atom. Along with the electron, there's another particle a bit like it, the electron neutrino, which they were in the news. Neutrinos were in the news a few years ago when experiments from CERN thought that they were traveling faster than the speed of light. You probably remember. Turned out not to be the case. Turned out to be a loose connection in one of our experiments. But okay, that's how you make progress in physics. So this is what we think of as the first family, the first generation of fundamental particles, and that's what you need to build ordinary matter that we see around us. But that's not the end of the story. There's a second generation, so there are 2 more quarks, the charm and the strange quark. They're just like the up and the down quark, but a bit heavier. There's a particle, again, like the electron, but heavier. It's the muon, and another neutrino associated with it. And we do see some of these particles around us in the natural world. So, for example, in cosmic rays. So cosmic rays are when there's been some violent event far out in the universe, and a charged particle has come towards us at high speeds, hits the atmosphere and starts interacting as it comes through the atmosphere of the Earth. So that's what you see here, a cartoon of a particle interacting as it goes and throwing off other particles. And what you can see from these events down at ground level include muons. So we detect them around us. That's not the end of the story either. There's a third generation of fundamental particles, so 2 more quarks, the top and the bottom quark, again, like the up and the down, but heavier still. A tau particle, which is like a heavy electron, heavier even than the muon, and another neutrino, the tau neutrino. And we don't see these particles around about us in the world. If you want to make and study those particles, then you need to go to facilities like CERN and Fermilab. So here we are. I mean, you're used to thinking for chemistry, you're used to thinking about the periodic table of elements, so organizing substances by their physical properties. And what we're building up here is a bit like a kind of periodic table of the fundamental particles. Fundamental because, as far as we can tell, there's nothing inside them. These don't have any structure, they just are. Okay, but I asserted early on that inside a proton or a neutron there are quarks, and of course you have a sense already of the length scales involved in these sorts of systems. So atoms are small, nuclei are pretty tiny, protons and neutrons are very small indeed, and I'm telling you that inside protons and neutrons there are further particles that are kind of unimaginably tiny quarks, and I hope the first reaction is, well, how can we possibly know this? And so to give you a sense of how we can understand this and measure these particles, I want to use an analogy of a snooker table. So imagine we've got some object sitting on this snooker table and we want to find out about it. Then one thing we can do is take snooker balls and start firing them at the object. So if we do that, it's pretty clear this is going to come straight back out at us. We can do it again with this one. Of course, that's going to come back as well. If we send this one in, well, that's going to go right through. And here's the sort of general case. If we hit the snooker ball off this object at some angle, then it's going to come off kind of like that. We can change the object. So here's another object. So we can keep on firing snooker balls in. And if we do that, well, that's going to go straight through, isn't it? If we manage to hit this object right on the nose there, then that will come straight back at us. And here's the sort of general case going off at some angle there. And you can keep on changing the object. That's going to go off like that, and so on. Okay, now let's change the situation. So for some improbable reason, there's now a board on top of the snooker table. It's balancing on these bits around the edge, so the balls can still roll underneath that board, but you can't see anymore what's going on. So there's still an object under here, and we still want to find out about it, but we can't see it anymore. So what can we do? Well, we can carry on firing snooker balls at it, and we can see how often the snooker balls come straight back at us, how often they come back at some sort of angle, and what that angle is, and how often the different angles happen, how often the snooker balls go straight through, and so on. And I put it to you that if you do that enough, then you ought to be able to work backwards and reconstruct what the object that you can't see under here is, particularly if you've done it many times with known objects, either for real on a snooker table or you've maybe written a computer simulation. And this unfolding problem, so working backwards from distributions of snooker balls bouncing off or going right through, working backwards to find out what the shape under here is, might be quite a complicated problem, but I hope you agree that at least in principle it sounds plausible that you could do that. Okay, so what's this got to do with understanding what is inside a proton or a neutron? Well, the problem is not so very different. What we want to know is a proton just a sort of blob, or has it got some well-defined structure? And in particular, is it made up of 3 hard components, quarks? So we need to fire something in to have a look. And of course, snooker balls don't help us anymore, but that's okay. We can find other particles to fire in, perhaps electrons, perhaps photons. And that's exactly what was being done at Stanford. So this is an experiment at Stanford in the 60s. So this is an accelerator that's a few kilometers long. So electrons start off here. They get accelerated along here to high speeds and smashed onto some target here. And pretty much whatever target you put there, there are going to be a lot of protons and neutrons in there. So it doesn't matter even so much what it is. Now, these are electrons, so we can't see electrons with our eyes anymore, but that's fine. We can build detectors that are designed exactly to do that, and that's what this is here. And if you can make out, see, this is mounted on big rails, so this whole thing can sort of swing round here, and that's exactly to measure these angular distributions that I was just talking about with snooker balls. So we take our electrons from here, we accelerate them to high speeds and smash them into a target, and then see how often they go straight through, how often they go off at some angle, and what those angles are. And from that, you can work backwards And you come to the conclusion that indeed, as I said at the start, the proton has got some structure. And in particular, the simplest description of that structure is as three hard objects inside. Okay, so that's trying to understand the matter part of the universe, if you like. But that's only one half of particle physics, because the other important thing is to understand how the matter particles, how all the particles interact with each other. And so to think about that, we need to think about forces. So if you want to describe the forces that fundamental particles can experience, then you can classify them into precisely four kinds. So the electromagnetic force, the weak force, the strong force, and gravity. So the electromagnetic force, of course, you're familiar with. You know you can feel the forces between magnets. Perhaps more importantly, the electromagnetic force is what keeps the electron bound to the nucleus. It's what lets us touch and feel things and see things. And the weak force is what is responsible for some kinds of nuclear decay, as you know, and also for preparing the sun. So this is a picture of the sun. And so the fusion reaction in the sun is a weak process. The strong force is the force that binds the quarks together inside the protons and the neutrons. And of course, gravity is what keeps us on the Earth and planets moving around the sun, and so on. And it turns out that when you try to think about these forces for fundamental particles, there's a fundamental particle associated with each of the forces. And so we really ought to have written those down in our periodic table of particles that we were putting together. And so here they are added in now, the W and the Z particles, and the photon and the gluon. And so the photon is the particle associated with the electromagnetic force. It's a particle of light. It doesn't have any mass. It's precisely massless. That will be important later on when we're thinking about the Higgs particle. The W and the Z particles are the particles associated with the weak force. So the Z particle is really quite like the photon, but it's really very heavy. And the W particle is heavy as well. And again, that's important for thinking about the Higgs particle later on. And the gluon is the particle associated with the strong force, called that kind of rather literally because it sticks the quarks together inside the proton and the neutron. And if you might have noticed that these four particles, I've only mentioned three of the four forces from the previous picture, and I haven't listed any particle associated with gravity. So we would like to have a particle physics sort of quantum view of gravity. That turns out to be complicated, and we've not any place close to describing gravity with a graviton, which would be a particle kind of analogous to this. That's really a story for another day. Okay, so here's a more complete kind of periodic table of particles. Again, the matter particles over here and the force carrying particles over there. So I said that if you wanted to make and to study some of these heavier particles, then you needed to go to a laboratory and use facilities there. And so I want to think just about how you do that. And actually what we use is what Einstein told us, that mass is just a form of energy. And what that implies is that if you can concentrate enough energy in a small enough space, so if you can create a large enough energy density, then you can create new heavy particles that have got some mass m that weren't there before. So if we think back to this accelerator from Stanford in the 60s, we were thinking about just electrons scattering, so being deflected through some angle when they hit the target. But when you start to introduce forces, you realize that electrons can do more interesting things sometimes when they hit this target. And not only can they just bounce off the target like snooker balls do, but they can actually interact in some more interesting way, and in fact turn some of the large kinetic energy that they have by the time they've been accelerated these kilometers up to here into new heavy particles that weren't there before. Furthermore, it turns out that if your main aim is to create new heavy particles that weren't there before, rather than just to understand what's inside the proton, which is what we started off trying to do, then you can do better than just smashing one beam of particles into a fixed target here. And the way that you can do better is to take one beam of particles and rotate it one way round a tunnel, another beam of particles and rotate it the other way around the tunnel, and then at some point you let the beams of particles collide. So at the moment when these counter-rotating beams of particles collide, you have exactly this situation that I was describing of a very great energy density, and then you have the possibility of creating new heavy particles that weren't there before. By their nature, if you create heavy, rare particles, they have a very short lifetime, they decay very quickly, and that's what these lines are supposed to represent. These are the decay products of particles created in the beam collisions flying away from the interaction point. So our latest and greatest machine for doing this is the Large Hadron Collider. Here's a picture of a sort of aerial photo of the Geneva region, and just to give you a sense of the scale, this is the runway of Geneva Airport here. So, I mean, the Large Hadron Collider is an understatement, really. It's not large, it's enormous. These are just circles drawn on the picture to give you an idea of the scale. You can't see this when you're there. The tunnels are about 100 meters underground, and they're 27 kilometers around the main accelerator here. It's a machine of astonishing extremes. So inside the machine, in order to keep the beams going round, it has to be kept colder than outer space. It's run at about 1.7 Kelvin. But then at the same time, when we create the beam collisions, the conditions that are created are hotter than inside the sun. And that's why you sometimes hear the Large Hadron Collider referred to as the Big Bang machine, because the sorts of temperatures associated with those collisions are the sorts of temperatures that were last ambient in the universe very shortly after the Big Bang. So if you were able to tag a proton, where it's protons that were colliding here, protons with more protons, and if you were able to watch one going round, it would whiz round about 10,000 times a second. So it's going 27 kilometers all the way around, about 10,000 times a second, so very close to the speed of light. The kind of engineering, astonishing thing. This is what it looks like inside the tunnel. And so most of these parts here, you can see curving round in the distance. Most of these elements are bending magnets, because if you have a beam of charged particles and you want to keep it going round in a circle, then you need to apply really very strong magnetic fields in order to keep particles going round and not just flying off. And the Large Hadron Collider is the last part, in fact, of a long chain of accelerators. So that's the Large Hadron Collider there. But it's fed by a whole series of other accelerators. And the reason for that is that it's just difficult to go from a standing start to very close to the speed of light in one go. So protons start here, and in each little bit along the way, they pick up a bit more energy until they reach full speed in the Large Hadron Collider. So let's watch the path of a proton starting from here. So it goes through the linear accelerator, picks up speed in the booster, then the proton synchrotron, another one starting, then the super proton synchrotron. The other one's going around the other way. They're both now in the Large Hadron Collider, and at some point we let the beams collide. And we have to try to capture what happens to understand. So here the particles come in again, create the very high energy density. New particles can be created, they decay very quickly, their decay products fly out, as I said, and then the challenge to an analyst like me is to to capture all of these decay products and work back to find out what happened at the moment of the collision and when exciting new particles were discovered, and try to pick out those events and measure their properties. And you can think of this a little bit like a three-dimensional digital camera. It's something like a 20 megapixel digital camera. And if you're good at digital cameras, you might not think that that's very impressive. You can buy a 20 megapixel digital camera, a 10 megapixel digital camera on Amazon for not very much money. But the difference between this and anything you've ever seen before is that we have to take the snapshots with this detector 40 million times a second. That's because we're looking for very rare processes. So only about maybe 1 in a billion times that protons collide are we actually going to make a Higgs boson. What happens when you collide protons is entirely statistical. You can't say today I want top quarks, tomorrow I want Higgs bosons, and so on. You just have to keep doing it. Some fraction of the time you'll get Higgs bosons, some fraction of the time you'll get top quarks, Z bosons, W bosons, whatever. And you then need to try to pick out from all of these snapshots that you take the interesting ones. And processes like the Higgs boson production are so rare that we just need to keep on doing it at a huge rate. Okay, so there are 4 of these experiments around the Large Hadron Collider. This is ATLAS. This is my experiment that I just showed you. There's another one across the ring from that, CMS. It looks very different, but it was built to make the same sorts of physics measurements. And then there are 2 more, rather more specialized detectors. The ALICE detector, that is actually for when the Large Hadron Collider is colliding not protons, but ions, so protons and heavy ions, or heavy ions with more heavy ions. It's built specially to measure those events. And LHCb, which is designed particularly to measure properties of the B quark. And so here's a sort of cutaway picture of my experiment. And you see it's built like sort of concentric layers of an onion, so shells of detectors that are designed to measure particular properties or particular particles in particular. So here's the collision point here, and then decay products from the collisions fly off in all directions, and as they go through each layer, they leave a small amount of energy behind, and that's what's supposed to be indicated by these blobs here. And then someone like me has to write software to kind of join the dots, to say, all right, it looks like all of these energy deposits along there line up. Let's call that a particle. And then we can look in more detail at the profile of the energy left, for example. Maybe this one left more energy in this part of the detector and less out here, whereas this one left a lot of energy out here. That helps me to say, well, I think this was a muon, or I think nothing else. And by doing that, then you build up the picture of what happened when the beams collided. And this is a sort of cartoon, but I wanted to show you just a picture of what some of these detectors look like. And I've picked some that the group in Glasgow was involved in designing and building. So this barrel here, this is this part, this little bit right in the center here. It's one of the tracking devices, and this wheel here is one of these wheels that you can sort of make out here. So bits of these detectors were designed and put together here in Glasgow before being shipped out and then installed in the experiment at CERN. Okay, I want to come on to the Higgs boson. So far, what I've been building up for you is a very experimental approach to particle physics. It's to say, well, we observe that there are these particles that we can classify like this, and if we build accelerators and collide particles at high energies, then we can create more and measure their properties, and they all kind of fit together like that. But I want to think for a moment, if instead I were a theoretical physicist, how I would come to construct a theory of particle physics and how that goes together with what we see here. Because Peter Higgs was a particle theorist. He's never really touched an experiment in his life, I suspect, not for a long time. Okay, and so first, I want to talk a little bit about symmetries in physics, because that's a very fundamental and powerful idea that really leads us to how to think about theoretical particle physics. So you know what symmetries mean in everyday life. So if you say something looks symmetrical, then it's probably got some sort of pleasing form. More precisely, it's maybe the same on one side as the other side. If you reflect it in a mirror, perhaps the mirror image is the same as what you see to start with. Perhaps if you rotate it, then what you end up with is what you started with, so that's a symmetry. And it turns out that symmetries are very closely related in physics to conservation laws. Now, so far I've only really talked about geometrical symmetries, so looking in a mirror or rotating something. But let's think about some more symmetries. So say I'm doing an experiment, and I do my experiment over here. Then other things being equal, if I now do my experiment again and I do it over here, I would expect to get the same result. Other things might not be equal. There might be a big magnet over here that wasn't over here, but if other things were equal, I would expect to get the same result. And that's a translational symmetry. Similarly, if I do my experiment this way around, and then I do my experiment this way around, other things being equal, I would expect to get the same result. If I did my experiment yesterday and I do it again tomorrow, other things being equal, I would expect to get the same result. So those are all symmetries. And it turns out that those things are closely related to conservation laws. So the idea that if I do my experiment yesterday and repeat it tomorrow, I ought to get the same result, that's mathematically the equivalent to a statement of the conservation of energy. To say, if I do my experiment over here, and then I do it over here, and I expect to get the same result, that's equivalent to a statement of conservation of momentum. And if I do it this way around or this way around, and I expect to get the same result, that's a statement of conservation of angular momentum. So these ideas of symmetries and of conservation laws are very closely linked. And so that brings us then to what you do when you try to construct a theory of particle physics. So let's start with one of the matter particles, say the electron, because we know we see electrons around us. So we write down some symbol for an electron. Then we have to think, right, we want to construct a theory to describe how this thing behaves. How are we going to do that? Well, we observe around us in the world that the various conservation laws, for example, that I just described, hold. So whatever theory we come up with, it better adhere to the principle of conservation of energy and of conservation of momentum and angular momentum and so on. Otherwise, it's a no good theory, because straight away we say, well, that theory doesn't correspond to the world that we see. And what I was just talking about was that these conservation laws are closely related to symmetries. So the way that you actually build these ideas into your theory of particle physics is to require that the theory that you're writing down obeys some symmetries. Now, the astonishing thing about particle theory, and what this shows is just what a powerful approach to understanding the world mathematical physics is that when you take your, for example, electron, and you say, right, I require that these symmetries hold, in other words, those conservation laws are going to hold in my theory. What emerges from that, what emerges from the mathematical structure of the theory, are the force-carrying particles. So in some sense, the mathematical structure of the theory predicts then that you have the particles like the photon and the W and the Z boson, and we know that they're there. So straight away you say, aha, right, this all looks very promising. This approach to trying to understand particles using mathematical physics, it looks like there's something right about it. And the theory that you come up with, which is very beautiful, it can be written on half of a t-shirt there, can be used to compute things that we can go and measure. And it can be used to compute things to astonishing levels of accuracy, so to the 13th significant figure, things that we can also go and measure to astonishing levels of accuracy, to the same levels of accuracy. And the theory and the experiment agree precisely. So I'm talking about the magnetic moment of the electron in particular. So there's something clearly very right about this approach to describing particle physics. But there's a big problem. And the big problem is that all of those force-carrying particles that emerged in the mathematical structure of the theory are exactly massless. Now, that's fine if you're a photon, because the photon is massless, but it's immediately a big problem for the W and the Z particles. Remember, I said that they're like the photon, but they're much heavier particles. But from this sort of straightforward approach, what you've got are massless particles. And it turns out to be very difficult just to introduce masses into the theory without spoiling all of the things that were good about the theory to start with, spoiling all those symmetries and conservation laws and things. And so that's what Peter Higgs was trying to think about in the 1960s. He was trying to find a way of including in this mathematical theory a description of the masses of the particles, the W and Z particles, and also the matter particles themselves. And what he came up with was what sounds like a very extreme approach to solving this problem. He and others, in fact, they came up with the idea at around about the same time, which was that the universe is filled with some sort of mysterious thing that we now call the Higgs field. Now, I think you're all used to describing forces through fields. So if you've got a magnet, then it creates a magnetic field that is experienced by other things around it. The difference with well, right, but then the important thing about that is that if you take away the magnet, you take away the source, then there's no field anymore. The difference with the Higgs field is that this field has a value everywhere in the universe, even where there's nothing else. The Higgs field is there and it's not zero. So then the idea is that all the other particles interact with that field, and that's actually what we mean by the masses of those particles. So if you've got particles that interact rather strongly with the Higgs field, that's what we mean when we say a particle is heavy. If a particle interacts with the Higgs field but a bit less, that's what we mean when we say it's a light particle. And if a particle doesn't interact at all with the Higgs field, that's what we mean when we say it's a massless particle. Now, that's all very well, but what we want to know is, does this idea, which works beautifully mathematically, solves the problems mathematically, does this actually correspond to any physical reality? And what we've seen in the mathematical physics approaches in the past is that the mathematical physics, the structure of the theory, is a good guide to the physical reality that's there. We got the force-carrying particles kind of out of the structure of the theory. So you might hope that this was going to be right again, but we need something to go and test. And what Peter Higgs realized, which none of the other theorists working in this sort of area realized, was that if there is a field like this throughout the universe, then there ought also to be a particle associated with it, and that's the Higgs boson. And you can think of the Higgs boson as being an excitation of the field. And that's a sort of language that we're used to in particle physics. So we think of a photon as an excitation of the electromagnetic field. Correspondingly, the Higgs boson is an excitation of the Higgs field. And so what we need to do is go away and look for a hint that that particle is there, that Higgs boson is there. And if we can find the particle, then that's a pretty good indication that the idea was right and that the field is also there. So that's exactly what we've been trying to do in the experiments. The theory had nothing to say about what the mass of the Higgs boson itself was, although it's closely connected to the masses of all the other particles. So we had to go and look for all sorts of different possible masses of the Higgs boson. But what the theory did tell us was how a Higgs boson of a particular mass would behave. And so here's an example. Here we're creating a Higgs boson from the collision of two protons or gluons inside the proton here. And one of the things it can do sometimes statistically is decay to two Z particles, and then we know how Z particles behave. Sometimes, again, according to statistics, some of the time they'll decay to other particles that are either electrons or muons. These are leptons here, either electrons or muons or tau particles. And so this is an example of a very distinctive signature, a footprint that would be left behind in our detectors if we produced some of these Higgs bosons. And this is a picture depicting some real data, collider data collected by my experiment, which is one of these, an event that looks very strongly like that. So here are the four particles, muons in this case, 1, 2, 3, 4 muons going away from the collision point. And so we can't say that this was definitely a Higgs boson created in here, but we can begin to build up a statistical picture and look for an excess of events like this compared to what we would expect if there wasn't a Higgs boson there at all. And so I've got a picture here of, just coming to the end. Start again in a moment. So as time goes on, we collect more and more data and analyze it. This will just start again. Right, so here we are back in 2011. We're collecting data. So data points are given by these black markers here. We've reconstructed the total mass of those four particles, electrons or muons, like in the picture I just showed you, putting them all together. And in red here, this is what we would expect to see if there was no Higgs boson there. That's the 2011 data. I think we're about to start getting the 2012. Oh no, that was all of it. And what you see is that an excess begins to build up here that's not described by the red picture here. And so this is the Higgs boson, and we can try then to add in this blue part here, which is describing the data using the addition of the Higgs boson. Okay, so all of this time, now you've seen it, so you know what to look for. You can begin to see this excess building up here. That's the Higgs boson appearing in the data. Now we're going to zoom in on this region here and fit the model that includes the Higgs boson to that data. And from that, you extract a measurement of the Higgs boson rates and coupling and mass and all these properties that we want to try to pin down. Okay, so we can look at not only that particular decay channel, the one that's shown here, but lots of other ones, and we can keep an eye on the significance of the signal that we saw building up there. And so as time goes on, we added more and more data. Oops, too far. And what we see is a very significant signal building up here, and that's what we called the discovery of the Higgs boson. So at first, we were only able to say we've discovered a new particle. It's definitely a new particle, but we didn't have enough of a sample of those things really to make good measurements and pin down its properties. And so that's what we're trying to do now, because what we want to know is, well, is this particle that we've discovered the simplest possible Higgs boson that you could write down in the theory, or is it maybe something more complicated? And in a way, it would be, well, it's very exciting to see anything at all, but it would be even more exciting to see something that was maybe not quite what we expected, because we know that there are a lot of questions that we're just not really addressing in our description of particle physics and the standard model of particle physics. So just to give two examples, we see around us a matter-dominated universe. We live in a matter universe. But if you think to what happened in the Big Bang, you would expect that as much matter as antimatter was produced. Now, I didn't really talk about antimatter. It's just the same as matter, but it's got the opposite electric charge. And so you'd expect that always to be produced in pairs. And then if you bring matter and antimatter back together again, then it annihilates and you just get energy. So if the same amount of matter and antimatter was produced at the Big Bang, you would expect that at some later time, it would all just go back together again and you'd be left with nothing. Now, that is largely what happened. We see in the cosmic microwave background radiation the the signature of a lot of matter and antimatter annihilating shortly after the Big Bang. But there's some asymmetry there, because what we're left with is a tiny amount of matter that was in excess over the antimatter, and that's the whole universe that we see today. And we can't explain, in our theories of particle physics, we can't explain that asymmetry to a large enough extent. We know about some sources of asymmetry, some places where matter and antimatter behave differently, but not enough to explain all the matter that we see in the universe. And another thing, well, we've got a matter universe, but what is most of it? Because what we're able to measure is that only about 5% of the universe is made of the sort of matter that I've been talking about all through this, the protons and the neutrons. We think about 28% of it is dark matter, so that's stuff that is interacting gravitationally, so we can see its effect on the large-scale motion of galaxies and things, but it's not shining at us. It's not sending photons at us. That's why it's dark. And we don't know what that is. We haven't got a particle explanation for that. And the rest, we call dark energy. We might as well call it X. We've really no idea what it is. So when we're measuring the Higgs boson and all the other particles that we do know about in the standard model of particle physics, we're not really looking to bolster the model. We're trying to knock holes in it to find the chink where we can then discover new physics and explain some of these things that we've just no idea about. And so the Large Hadron Collider has been running for a few years. It's expected to run for about 20 years more, and these are the sorts of questions that we're trying to answer. So just, I mean, in the final minute, just two things that I'm excited about today. One, this is a photo from Tuesday. This is the pit, this is the top, so this is the ground level, but the pit above my experiment, the Atlas experiment, and this is a new bit that's just going down. It's called the insertable B layer. It's a new bit of silicon that's going into the very center of the detector, and will be there and taking data when the accelerator starts again next year. It's off just now for a whole lot of upgrades and for things exactly like this. This was Tuesday, and then yesterday, this is it. This is this long tube, but just the end of it now, because it's almost all the way into the very heart of the detector. So it's very exciting to see these new things going in. And then the second thing I'm very excited about is the International Linear Collider. So this is a project I'm working on. Indeed, next week I'll be talking to my colleagues all over the world about the physics and engineering plans for this. This is the next step. So we hope that maybe beginning in 2016, we're going to build this machine in Japan. If we start, then we'll get the first beam in 2025. So these are massive long-term projects. But if we can build something like this, that'll let us really pin down the properties of the Higgs boson even better than we can do at the Large Hadron Collider, and I hope lead us to all the new physics, new effects. Okay, so that's pretty much it. I hope I've given you a sense of what I think we're trying to do at Hadron Colliders, what the Higgs boson is. The Higgs story is really remarkable. What Peter Higgs predicted was something entirely new. The Higgs boson's an entirely new kind of matter. You know, his prediction wasn't just seeing some sort of sequence 1, 2, 3 and predicting 4. It's really something entirely different, and that's why it's a real breakthrough, and why it's so exciting to see, and why he got the Nobel Prize for it. And so it's just the beginning of the story for the Higgs boson. We're trying to really measure all of its properties now, and as I say, I hope that we're going to see lots of new physics in the next years at the Large Hadron Collider and things like the International Linear Collider as well. Right, that's it. Thank you very much. Yeah, absolutely, of course.
Rhoda's asked me to introduce myself. I'm the West of Scotland coordinator now. I think we're from the so I deal with Inverclyde, all of the air shows on Argyll and Bute. Rhoda's also asked me if I can invite you to ask questions. Anything they want to ask, then this is your opportunity. It's great answer.
So it will be in early 2016. it gets to the highest energy, the design energy impact. So you would remember when it first turned on. I was in the control room that day, and no one had anything to do. We thought it was just some fault on a sensor, but we didn't believe that it was possible. So the upshot of that was some repairs, and since then the accelerator has not run at the power. The work that's been done over the last year should get us up to a centre of mass of close to 13 or 14 TeV, and that's compared to the 7 or 8 TeV that we've been running at so far. So that's exciting as well, because any time you push the energy frontier, you have this opportunity of crossing the thresholds where you can produce particles that you just didn't have enough energy to produce before. That's how we got the Higgs. We didn't have enough energy to produce it at the temperature on Earth. So anytime you have new energy frontier, you open it.
You mentioned the trip.
I haven't, because that's all sort of underway right now. So it's a bit late for this year, but it's a good point. So this is now the 4th year we've run a competition at Glasgow University that takes between 10 and 12 kids to CERN for 3 days. So again, I hope you saw that advertised on and I encourage you to consider pushing your kids in for it with the caveat that the funding that we have for the project is supposed to be directed towards sort of areas where opportunities are perhaps lower.
That's great, thanks very much.
Okay, well, I'll be around for